Hello, everyone who is coming into the webinar. We will get started in a couple of minutes when we've got more people in. And hello, everyone who's coming in. I'll just give it another minute or two as more people come in. Alrighty, numbers have slowed, so I think we'll go ahead and get started. So thanks so much to everyone for coming to today's webinar. Before we get started, I would like to acknowledge the traditional owners of the lands on which I'm located, the land of the Wurundjeri Woiwurrung people of the Kulin Nation. I like to pay my respects to their elders past, present, and emerging. And for anyone who's attending, if you would like to share the lands on which you're dialing in from today in the chat, please feel free. My name is Julianne Tice. I'm a Buildings Policy Advisor at the Energy Efficiency Council, and I'll be your host for the next 90 minutes. For anyone who's not familiar with the Energy Efficiency Council, we're Australia's peak body for smart energy management and demand response. So just to give you a little bit of scene setting for the webinar before we go over to our speakers, this is, I think, kind of a natural flow on from the last webinar that the EEC held on resilient cooling and heat stress in homes. That was in November last year. If you didn't get a chance to have a look at that webinar, highly recommend it. We'll drop a link to that in the chat. So today we'll be talking more about the comfort aspect and a little bit more about energy upgrades in homes, less the cooling specific and heat stress specific, but more general comfort and energy upgrades to go along with that, as well as occupant comfort. So we are going to be talking kind of about these two main aspects, being energy upgrades and occupant comfort. And specifically, we'll be talking about a concept called adaptive thermal comfort. I'll leave the detail on that to the experts because we do have two experts on that in today. But in layman's terms, the way I understand it, it's the idea that building occupants adapt to indoor environments, both physically and psychologically, and regulate their behavior based on indoor temperature. And this is a really important complement to the goal of energy upgrading every existing building. So we have this really ambitious goal in the built environment sustainability sector to optimize all buildings for low or zero emissions. And this is a really important goal. We do need to upgrade the thermal envelopes of lots of buildings, not just homes, but commercial buildings as well. And that includes upgrading the insulation, doing some air sealing, making sure there's proper ventilation, but also upgrading appliances to make sure they're efficient and electric and can run on renewables. And the EEC has been doing a ton of work on this front. So we'll drop links to our insulation roadmap and our recent report with A2EP on heat pumps in the chat. So we obviously really stand behind these technologies. I think they're really important for upgrading buildings and making them as low emissions and least impact on the climate and the environment as possible. However, we do need to acknowledge that this is an absolutely massive task, and the longer we take to get deep into this task, the more difficult it will be to complete it successfully. We're really running out of time to reach our net zero by 2050 goals, and the IPCC sent us or released another reminder to us all last week with their most recent report. So I'm not at all saying that we should reduce our ambition on this topic. We definitely need to get started as soon as we possibly can and ramp up our ambition as much as possible. But we do need to prepare for the possibility that we might not be optimizing every building as much as we might like to. And we are going to be facing increasing temperatures due to climate change. So we need to prepare for the rising indoor temperatures that we'll face as a result, particularly if we aren't able to optimize every building. And I'm thinking, of course, specifically of the very poor quality buildings, like many of the share houses I've lived in this country that are very leaky and uninsulated and horribly uncomfortable, especially in the depths of winter and summer. So today we're going to be talking about as I've said, improving thermal envelopes through targeted upgrades, but we'll also be discussing the need for adaptation to a wider range of temperatures, plus tools that we all need for coping with higher indoor temperatures. And we will be covering both residential and commercial buildings in this session, but each of our speakers more or less specializes in one of the two sectors. So we'll try to combine those conversations to be applicable to the entire building sector as much as possible. And I would like to also thank the Department of Climate Change, Energy, the Environment, and Water for their support on this webinar. So DECU supports the Energy Efficiency Council on the EEC's work to enhance Australia's engagement in the International Energy Agency's Energy in Buildings and Communities Technology Collaboration Program, or IEA-EBC. So DECU has made this webinar possible through that support. And I'll introduce my speakers in a second, but the first two presentations, or the first presentation you'll see from our first two speakers are coming from IEA-EBC. So we are recording the session. We will send out the recording next week. So in case you need to drop off early, or if you had any colleagues that are not able to make it at this time, we will be sending that out next week. So don't worry about that. If you have any questions as we're going along, please put them in the Q&A. Feel free to say things in the chat as well, but reserve any questions for the Q&A if you will. We'll get to as many of those questions as possible in the Q&A. So for now, I will introduce each of our speakers, who will then give a brief presentation, and then we will get into a panel discussion. So first, I'd like to go to Richard Didier and Jungsoo Kim. So these two speakers are representatives of the IEA-EBC program's NX69, Strategy and Practice of Adaptive Thermal Comfort in Low Energy Buildings. Richard Didier was one of the two operating agents for the IEA-EBC NX69. Richard is Emeritus Professor at the University of Sydney School of Architecture, Design and Planning, where he's Director of the Indoor Environmental Quality, or IEQ, laboratory. He's been active in the research domains of thermal comfort and IEQ since 1981, and is now the most highly cited researcher on these topics in the peer-reviewed literature. And Jungsoo Kim is a member of IEA-EBC NX69 and senior lecturer in building science at the University of Sydney, where he runs a postgraduate program in high performance buildings aimed at producing built environment professionals. Jungsoo's research is focused on finding ways to improve occupant experience, such as comfort, health, and productivity, while reducing associated energy use in buildings. He has research expertise in indoor environment, post-occupancy evaluation, and occupant behavior. And with that, I will leave it over to you two for a brief presentation.
Thank you very much, Julianne. And thank you to the audience for attending today. I'll just share my screen and introduce the NX69, which we were part of since from 2015 through to about 2022. So it's quite a long-running project. And I'll just go into presenter mode. So the title of the annex was Strategy and Practice of Adaptive Thermal Comfort in Low Energy Buildings. And adaptive thermal comfort has been identified as a key strategy to rebalance the need to reduce building energy use with the fundamental requirement to provide comfortable indoor environments for occupants. We have copious evidence from countless building science studies around the world that showing that strict temperature control drives energy demand and greenhouse gas emissions from buildings without necessarily benefiting the comfort and health of the occupants of those buildings. The adaptive thermal comfort concept provides criteria and inspiration for the design and operation of low energy buildings. So just to give you a very brief overview of the concept of adaptive thermal comfort, I think anybody in this field knowing a little bit about thermal comfort will understand that it's a response. It's a subjective response to the indoor climate of buildings. And the indoor climate of buildings obviously interacts with the heat balance of the occupants of the building. And the response of the physiological processes in the occupants, along with the physiological, thermoregulatory processes, drives the perception of thermal comfort, or rather thermal discomfort. It's often said that there's no such thing as thermal comfort. There's only an absence of thermal discomfort, and that's probably true. So anyway, that conscious perception of thermal discomfort is the driver for behavioral thermoregulation, where we actually get up and do things in the indoor environment, open a window, change our clothing, etc., etc. And in so doing, we modify the indoor climate, again, of the building, and that sort of completes in a negative feedback loop the concept. Now, I guess the key point in this little schematic of that negative feedback loop are these orange labeled processes. One is expectations, and the other one is cultural norms. And so in many ways, these sort of, you could almost think of them as set points on this automatic regulatory system. They're not fixed. They're not static. They actually can change. They do change. We've all witnessed them change. From my childhood in the 1960s to now, we've seen the penetration of air conditioning in the residential sector go from absolute zero to probably 80%. So, comfort expectations have changed profoundly. And likewise, cultural norms, clothing expectations inside building, that all changes as well. The level of business clothing, the strict regulation of business clothing in office workplaces is a perfect example of that. And it can change. In Japan, a couple of years ago, they relaxed dress codes inside office buildings, so people could wear casual clothes to the office, and that enabled them to change the set point for air conditioning in summertime in Tokyo, in Japan, up to 28 degrees Celsius. So my point is that nothing is set in stone with thermal comfort, that it is adaptable. We are adaptable. So the annex, as I was describing earlier, ran from 2015 to 2022. We had two operating agents, myself from Australia and Professor Yingjing Zhu from Tsinghua University in Beijing. We had 48 participants from 12 countries, including Australia, Canada, China, Denmark, Germany, Japan, Korea, the Netherlands, Norway, Sweden, UK, the US. And we also had participation from India, even though they're not actually part of the IEA. And I won't do introductions of all of these participants, but we had several expert meetings over the course of that 7-year project, where we came together face-to-face to sort of progress our deliberations. And the achievements over that period, it all came to a conclusion mid last year. And well, we had 7 expert meetings: London, Beijing, Ahmedabad, Seoul, Vancouver, Harbin, and Copenhagen. Not in Australia, because we don't get funding for IEA activities here in this country, but in other places, that's perfectly normal. We also produced 2 special issues of scholarly outputs in the peak research journal, Energy and Buildings. A total of 60 publications came out in that journal from this annex. And we also produced 4, for the final report of the project, we presented it as 4 deliverables, which were titled, number 1 was the development of the ASHRAE Global Thermal Comfort Database, Mark II. The second one was models and criteria for the application of adaptive thermal comfort in the built environment. Deliverable 3 was guidelines for low energy building design based on adaptive thermal comfort concepts. And number 4 was guidelines for personal thermal comfort systems in low energy buildings. Now, just before we launched this webinar this afternoon, I got a notice from the executive committee chair of the EBC saying that the final reports, these deliverables that you see on my screen, will be available on the official IEA EBC website imminently. I think probably sometime later today. So you'll be able to track those down if you want to follow up. So I think I'll leave it there for the introduction to the annex. Julianne.
Great, thank you so much for that, Richard. So next we will get to Veronica. So Veronica Soebarto joins us from the University of Adelaide, where she leads the Sustainable Urban and Regional Landscapes theme of the Environment Institute. She also leads the Sustainable Futures theme of Adelaide Nottingham Alliance, and she's the first CI of 2 ARC discovery projects on improving thermal environment of housing for older Australians and on developing resilient housing for low socioeconomic older people. She's also a CI of an ARC linkage project on determining the social value of extreme mixed-use urban environments. And with that, I will pass it over to Veronica. I think, Richard, you might need to stop sharing your screen so Veronica can then share hers. Thank you for that. And Veronica, if you want to fire up your video, we can go into your presentation.
Thank you, Julianne. I cannot turn on my video from this end, so if people would like to see me, I guess, Julianne, you need to turn on my video, but it doesn't matter. You don't need to see me. So thank you, Julianne, for this invitation. So I was asked to talk about the lived experience of thermal comfort. As Richard already said, that there are factors that are affecting our comfort, just put down in the front there, in terms of the environmental parameters, temperature, humidity, radiant temperature, and airspeed, as well as our activity, so the human factor, activity, and clothing. However, based on our research, there are actually a lot more personal factors that affect our thermal perception, as well as what we do in response to our thermal environment. So in addition to cultural aspects that Richard already mentioned, other personal factors such as financial situation, I guess the cultural includes knowledge and belief, but also we found there are some differences in terms of the people's comfort perception and behavior according to the age, as well as health conditions. And also in regards to where they live. So it's, I guess, again, it relates to culture, but also the climate. So acclimatization also affect that. So I just want to show 3 examples of the projects that I was involved or I led in the past several years. The first one is a project actually also with Richard many years ago. We were involved in an NCAP project looking at or developing a framework for adaptation of Australian household to heat waves. One of the housing development that we looked at in Adelaide, so this is our Adelaide team, was this low-income housing. And it's actually the first low-income housing in South Australia that has 7.5 stars, 7 to 7.5 stars. So, 11 years ago, this is quite advanced in terms of building performance. What I just want to show here on the top right hand here, we analyzed the data, and one of them was looking at their mean thermal sensation vote. So when they feel neutral, so 0 is neutral, 3 is hot, -3 is cold. And then based on their votes, because we put temperature sensors, humidity sensors, and so on in the house, so we can find what happened in the actual house, the indoor environment. And we found using the, based on the relationship between the thermal sensation vote and their indoor temperature, we found what we call the neutral temperature, the temperature theoretically when they don't feel cold or hot is 21.7. So just keep that for now. And then when we look at when they feel neutral, it is actually within the acceptable limits of the adaptive model that Richard developed and is part of the ASHRAE standards. Although, as you can see, there are some times where people say they're neutrals, but the temperature is actually above the limit. But what I like to point out is, as I mentioned, the houses, actually, the units are all 7 to 7.5 stars. However, this is low-income housing. Now, as you are aware that with the 7.5 stars, that means their total heating and cooling load is lower than what 7 or 7.5 stars band is, which means it performs quite well. In other words, their heating and cooling load is quite low, theoretically. However, that means they still need to use heating or cooling to be comfortable. In reality, that's not what happened. We only look at the study, the study is looking at summer. As you can see, there are times when the temperature was above that limit. It even goes to 32, 33 degrees when it was also quite warm outside. And the main reason for that is they simply cannot afford running the air conditioning. So there was an air conditioning unit installed in the living room, but very rarely they turn it on. And they had to rely on opening or turning on the fan. That's the first strategy, open and closing windows and so on. So turning on the AC is kind of low down the list. The second example is in our previous study and also the current one looking at housing of older people, where we look at or we meet or we talk to 300 over 300 older people, did focus groups, but mostly we more importantly in this case is we monitor 60 houses involving about 80 households. And we did it over 9 months, so covering summer, autumn, and winter period. Similarly, we put environmental data loggers inside, monitoring temperature, humidity, and so on. And we asked people to answer questions about their thermal comfort, preference, activity, clothing, and so on and so forth. And what we found, again, looking at the relationship between the mean thermal sensation vote to the indoor operative temperature, we found this correlation. And as you can see, if you compare it with the previous study where it's actually most of the occupants are actually not 65 years or over, as you can see, the slope of that relationship is quite different. And their thermal, neutral temperature, excuse me, for the older people is much higher than what we found earlier. And looking at this, you can tell, or you can probably assume that also this is based on other studies that as we get older, our thermal sensitivity might be reduced. So people just don't feel as much as or as sensitive as we were when we were younger due to changes in our metabolic rate, our physiological condition, and so on. And interestingly, when we talked to them, they also said that, I feel the cold and I feel cold more than I was younger. Although in this case, they said the heat doesn't affect me as much. Although some other people would say they prefer the heat to the cold. So it really varies, but overall, that's what we found. What we also found that it is possible that the difference between the older cohort results in their thermal sensation is also affected by their adaptive behavior. Once again, they use a lot more personal behavior to react to the thermal environment by putting, for example, more clothing. This is the relationship between the clothing level and the indoor temperature. You would see that there are a lot of times when the temperature is actually quite low, and they simply put on more clothes rather than turning on the heater. Likewise, when it's warmer, they just put less clothing or they do less activity when it's warmer. And there are other strategies that they put, and I just put in some of the quotes here. Some of them say they put a block of ice in front of the fan, or again, they change the diet, more warming food in the cold climate or cold environment, and then light food during summer. And this is my favorite quote. This person lives in Whyalla, which is in the part of the hot arid climate. She said, the way I keep cool is into the freezer. I've got a shelf in the freezer that I have 2 dresses during summer. One goes to the freezer and one of them I put on. After an hour or so, I changed them because the ice melted, and I know I always got something cold. When my air conditioner broke down, that was godsend. So again, majority of the older people had concerns about running their air conditioning because they acknowledged that the electricity prices is getting higher every day. So again, their adaptive behavior is more what makes them feel comfortable rather than simply turning on the air conditioning. We also found that there are even more factors. So we collected so much data on their demographic and other personal factors. And we did statistical analysis and found significant factors that affect their comfort as well as behavior, whether or not they have concern about the cost, the age of the house, whether they live at home or at the retirement, whether they're frail or less frail. Once again, income is another factor as well. When we look at the whole cohort, we were able to kind of look at using cluster analysis as well. Then we were able to identify 6 thermal comfort clusters in a way, although if you look at it carefully, it's probably only 3. So one is actually, this is the relationship between outdoor and indoor. One is the cohort that preferred warm all the time. Another one that the cohort that is more responsive to the outdoor environment and they can adapt to it much better. They tend to be the ones that are more active rather than compared to the ones that prefer warm condition. They tend to be those who were less active, has health conditions. And then the rest of the cohort was the one that probably you could say is a bit less sensitive to, and this is similar to what I showed before. So kind of 3 cohort there. Finally, I just want to share one more study. This is done by our PhD student looking at housing in hot, humid climates in Darwin and surrounding areas, involving about almost 40 households and doing 21-year monitoring. As you can see here, that the slope of the relationship between their thermal sensation and operative temperature is perhaps similar to what we found in Adelaide, except their neutral temperature is much higher than what we see in Adelaide. So as you can see again, that the adaptation to the warmer condition means that they can tolerate a much higher temperature. When we see what they do, they similarly, most of the household, majority of the household would turn on the fans first. In Darwin, we found that the air conditioning is the second option, whereas in Adelaide, because it's not as hot as in Darwin, it's actually down the list. But as you can see, turning on the fan is so important to be comfortable, even in a hot, humid climate such as Darwin, and other activities such as clothing and go outside and so on, I guess are kind of similar. So that's all that I like to say, but I guess my main point is, as Richard mentioned at the end of his presentation, that thermal comfort is really not a straightforward issue. Hence, my view is using thermal comfort theory, for example, in building code to estimate heating and cooling and therefore assess energy efficiency of design needs to be done really carefully by considering the possibility that they are quite different between areas, between region, age, and perhaps any other factors. And really, there's no one size fits all, and which I think make the issue of thermal comfort really interesting. Thanks, Julianne.
Thanks for that, Veronica. It is really super interesting. I think we're already starting to see quite a few examples of the differences that people experience, the way different people experience comfort, and all of the different factors that factor into how they experience comfort. And we've already got a point in the chat, which is quite right, which is around the conditions of commercial property leases and how comfort might tie in with that, which is hopefully something we'll get into in the panel discussion. But for the moment, I will go next to Toby Cumming, who is the team leader for research and evaluation at Sustainability Victoria. After completing a Bachelor of Behavioural Science at La Trobe University in Melbourne, he went to the UK to undertake a PhD at Cambridge University. Returning to Melbourne, Toby worked for 12 years as a research fellow at the Florey Institute, focusing on stroke and dementia. And in 2019, wanting to make a greater contribution to the fight against climate change, Toby shifted to Sustainability Victoria to work on the Victorian Healthy Homes program. I think that's one of the best bios, with that great shift from one potentially you could think unrelated area to sustainability, but as we'll probably see, it's very much related in terms of that research background. So Toby, take it away.
Thanks a lot, Julianne. Great to be here. I'm just going to share my screen too to show you some slides. Okay, so what I'm going to be talking about today is really about cold temperatures and being too cold in winter. And I wanted to start with why this matters. This is one of my favourite studies from Europe that looked at various different regions in Europe back in 1997. And they found, probably unsurprisingly, that cold-related mortality was associated with lower indoor temperatures, so lower average living room temperatures, but somewhat counterintuitively, higher average winter temperatures outdoors. So when we looked at comparing a couple of places, Finland in the cold north and Athens in the temperate Mediterranean, you can see here that the cold-related mortality is actually much greater in Athens than it was in Finland. So every per 1 degree below 18 degrees, the increase in mortality greater in temperate Athens. And a lot of this has to do with building quality. So when they measured average temperature inside, when it was 7 degrees outside, fully 2.5 degrees warmer in Finland than it was in Athens, because their buildings are built for the cold. As Julianne said, we've got lived experience of this in Australia, particularly in southeastern parts where it's not balmy tropical Australia. It's actually quite cold for 4 or 5 months of the year. So I'm going to talk to you about the Healthy Homes program we did in Victoria. Really, this started and was inspired by research that happened in New Zealand in 2007 and 2008. So there was a randomised trial. They looked at putting insulation in homes, pretty cheap, readily available intervention, and found really impressive health effects. So kids going to school more, adults going to work more, fewer GP visits, etc. In the context of today's talk, I thought it was really interesting to have a closer look at their temperatures. So these temperatures were really cold. Admittedly, these are bedroom temperatures I'm showing you here, not living area temperatures, but this is average across the households. Before the intervention, 13.5 degrees, so very, very cold. After the intervention, you notice there's not a massive change, 0.6 of a degree, about half a degree resulting from the insulation that went in. But when you look at the subjective experience, these householders were asked, is your house cold most of the time or always? You can see there the vast majority before the intervention said yes, it was. But after the intervention, less than 100 out of 550 said yes, it was. So the point here is that half a degree can really matter to subjective experience. Here's what our program looked like. So Healthy Homes delivered 1,000 upgrades to low income and people with health needs across Victoria. But the novel part about it was more than a delivery program. It was a randomised controlled trial, and here's the design of it. Household expressed interest. We checked their eligibility. We went to visit them, asked some questions. Then we did the residential efficiency scorecard to map what their house looked like in terms of efficiency, randomised them to intervention and control. So everyone received the upgrade. The only difference was the intervention group received it before winter and the control group received it after winter. And that allowed us the 3-month winter period to make a comparison between homes that had already been upgraded and those that hadn't yet been upgraded. And we were interested in things like temperature, energy use, but also importantly, health and quality of life. So here's what we found in terms of temperature. Our intervention, it's important to note, was pretty minor, so less than $3,000 a house. It wasn't a very deep retrofit. And we made intervention homes 1/3 of a degree warmer, which was significantly different to the control homes over winter. Importantly, this impact was greatest in the morning when homes tend to be at their coldest. So we raised them by about 1/2 degree between 8 and 12 in the morning. And in terms of time, less exposed to cold. So the WHO sets 18 degrees as a reasonable temperature to maintain health over cool seasons. That was 43 minutes a day less exposed to cold in the upgraded houses. But we know, and I'm sure we'll talk about this in the Q&A, objective temperature measurements don't always equate with subjective experience. Veronica mentioned there's other things like airflow and humidity that can affect thermal comfort. When we asked specifically about thermal comfort, the intervention group were more than twice as likely as controls to report they felt warmer. So this maps onto those New Zealand results really nicely, that doing the upgrade makes people's subjective experience of warmth better too. A breakdown by the residential efficiency scorecard here, which goes from 1 to 10, with 10 being the most efficient houses and 1 being the least efficient houses. It's not hard to see the relationship here with indoor temperature. So you can see if you're living in a 1 or 2 star house, you're likely to be very cold, whereas upper end of the scale, they're all pretty much sitting with averages above the recommended 18 degrees. So this is really where we need to focus our efforts and our retrofit programs on the worst houses out there. So just to conclude, in Healthy Homes, we were really focused on winter warmth and increasing thermal comfort over winter, not just as a comfort thing, but as a health intervention. We found greater quality of life as well across mental health and reduced social care needs between the groups. Even though we increased temperature, this wasn't by pumping more energy use into houses. We actually significantly lowered the gas use through our intervention. So we know we're making an impact on the thermal shell here, which is the important thing. And if you're not looking at health outcomes and health savings as a result of this, you're really missing a huge portion of the puzzle, because for every $1 we saved in energy, we saved more than $10 in health, which meant that it had pretty impressive cost effectiveness, paying for itself in less than 3 years. So that's all I wanted to present. Back to you, Julianne.
Thanks so much, Toby. That's really an outstanding figure, that $10 savings for every $1 of energy savings. Pretty much floored us all at the Energy Efficiency Council when that report came out. So that's super exciting. I will ask our other panelists to come back on screen and we'll get into the panel discussion. So first, I will go back to Richard for a question on these principles of adaptive thermal comfort and how they relate to, I guess, historical means of measuring comfort. So I think you didn't go into these conventional measures of comfort, but it popped up on your screen at the very end of your presentation. So those measures being predicted mean vote, or PMV, and predicted percentage of dissatisfied, or PDD. If you would like to really quickly explain those and how adaptive thermal comfort presents an alternative to those conventional measures, and how can the principles of adaptive thermal comfort specifically be used to help us understand when the efficiency of an existing building must be improved, or when occupants can make changes to themselves or to their own environment to improve their comfort.
Very quickly, I'll show another slide or two, and tell me if you can see what I see. Another red screen.
Yes.
So talking about the conventional indices of thermal comfort, the ones that probably have dominated HVAC engineering for at least half a century are the ones that Julianne just mentioned, PMV and PPD. PMV, the acronym stands for Predicted Mean Vote, and it's an algorithm that estimates on the basis of 6 input parameters how a particular environment, indoor environment, will feel on a 7-point thermal sensation scale of the type that we saw in Veronica's presentations. It's predicted mean vote, so it's referring to the mean person or the average person, which obviously there's no such being, but so that's the first point I wanted to make, that it is just an estimate of the middle person in a spectrum, if you like, of thermal comfort requirements. You could think of that spectrum as being like a bell-shaped curve, and PMV is trying to hit the middle, the peak in the bell-shaped curve, but it completely ignores the, I won't even say the tails, but the large amounts of the population, large percentages of the population that sit outside that central plus or minus 1 standard deviation. Now, the PPD is where it gets really interesting. And the PPD is itself a, oh no, sorry, before I get to PPD, I just wanted to refer to the concept, if you like, the theoretical concept behind PMV, PPD. And it's basically looking at the relationship between occupants and their indoor climate in a very linear, deterministic sort of way, where the physics of the internal environment affect the physiology of the human body, which in turn affects the perceptual processes, and voila, we get a thermal comfort outcome. But there's no feedback in that approach, and it completely ignores that essential feedback dimension that I was trying to highlight in my earlier slides. Now, you could artistically, you could represent that very deterministic, linear, open loop as this little character sitting in a glass box with no capability of regulation of their thermal environment, basically putting up with whatever they're given. And so how does the predicted mean vote relate to the predicted percentage dissatisfied? Well, it's based on this idea that if the PMV is 0, that is, the average person feels neutral, neither warm nor cold or cool, the predicted percentage dissatisfied, based on this idea of the bell-shaped curve, will be 5%. What that says is that you can't please all of the people all of the time, at least according to Fanger 50 years ago. And he was probably right. You certainly can't please all of the people all of the time. The 5% thing is probably an incredibly optimistic view. I think time and time again, we've seen in building studies, in real buildings, not theoretical calculations, but actual field studies with real building occupants, the minimum dissatisfied is about 20%. And very often we see it as high as 40 or 50% dissatisfied, when theoretically they should be only 5%. So that's the concept of predicted mean vote and predicted percentage dissatisfied. Why has it been so popular, and why is it so widespread in terms of standards and practices in the HVAC industry. And the only explanation I can come up with is that it's really attractive in its simplicity. It gives a nice quantitative answer to the questions that an engineer wants to ask at the design stage. So they do a building simulation, calculate indoor temperatures, put the PMV calculations through those indoor temperatures and conditions, and voila, get a PPD. So as a design tool, it's fabulous. It's really, really helpful. Unfortunately, it doesn't actually work, but that small detail is often overlooked by practitioners. So, which brings us to the alternative, which was a bit of a heretical concept way back in the 90s when we launched this idea. I did it with a project for ASHRAE with a colleague of mine from Berkeley, Gail Brager, and we were commissioned to look into the development of an adaptive thermal comfort approach, which is the full-blown self-regulatory feedback sort of concept of thermal comfort, where the occupants are actually actively engaged in and part of the internal built environment. Anyway, the upshot of that project was a standard, a proposal for a standard that was, we proposed on the basis of the empirical analysis that we did in that project for ASHRAE back in the 90s. We proposed something that you can see on the right-hand side of my screen here. It's referred to as ASHRAE Standard 55. And after many years of haggling with the Standards Committee, they actually accepted it, and it's been there ever since. It's in the latest version of ASHRAE 55 in 2020. And what it does, it just says, on the basis of an outdoor climatic condition on the x-axis of that graph, you can predict a range of internal temperatures or internal operative temperatures that will be acceptable to 80% of the occupants of that naturally ventilated building. And just recently, they've expanded the scope of that standard from naturally ventilated buildings to hybrid ventilated buildings. So that was way back in 2004 that ASHRAE took that bold step. And then Europeans, being Europeans, decided that they didn't want to follow an American precedent. So they reinvented the wheel, did their own adaptive comfort model, came up with an almost identical ASHRAE, adaptive comfort standard that you see over on the right-hand panel. And it's the same concept, basically. A given outdoor climate will enable you to estimate what an appropriate indoor range of temperatures would be. So I'll break there and turn it back to Julianne for discussion.
Thanks for that, Richard. So I'll go to Jungsoo next. So Jungsoo, I want to deviate from what the expected question was a little bit, but if you can't answer this question, we can definitely go to what the plan was originally. But I'm wondering, so Richard's been talking a little bit about how buildings have been designed with these conventional measures of comfort in mind. I'm wondering if that's still the case for buildings, whether it's commercial buildings or residential buildings or both. And are there any moves in Australia or elsewhere in the world to employ these adaptive thermal comfort principles in designing and constructing new buildings?
Thank you, Julianne. That wasn't the question that I was expecting to hear from you, but yeah, there is a movement trying to accommodate this adaptive approach in building design and operation. And that was actually one of the concepts underlying in Annex 69 activities. So we wanted to challenge this misconception that the more energy we spend, the better comfort can be achieved. But that's not necessarily true. And this was the concept that we really wanted to challenge through the Annex 69 activities. So one of the subtasks in Annex 69 was to demonstrate that it is possible to achieve a good level of comfort without having to use air conditioning all year round. So there are more than a dozen case studies carried out by participating countries in different parts of the world in different climate context. And they all picked an example of building, which is kind of built on this adaptive comfort model concept. So in those sample buildings, there were plenty of opportunities for occupants to practice adaptive opportunities. And most of those buildings were mixed mode buildings. I mean, it has a hybrid approach utilizing both natural ventilation and air conditioning if the outdoor condition was not that favorable. So, and we've consistently found across all the case studies, what was common was that in these buildings that were not heavily relied on air conditioning to provide comfort indoors, and the indoor temperature often drifted far away from what we know as the optimal comfort conditions. But in those buildings, occupants still found themselves quite comfortable, or they managed to maintain their comfort. And common features in all these case studies was that these buildings had good adaptive opportunities available for occupants to practice, such as access to window, access to fans, and also, more importantly, quite flexible clothing. So there were no strict rules around what they should wear to their work. So, and occupants in these buildings, they actually took these opportunities as an active agent, as Richard explained in the adaptive group, and they used them to maintain their comfort. So, there seems to be a misconception that thermal comfort is achieved by regulating temperature. And to regulate the temperature, usually our first choice is to use an air conditioner. But changing temperature is quite energy intensive. And referring back to the PMB model that Richard introduced, and also it appeared in Veronica's slide, temperature is only one input parameter out of half dozen variables that shapes our comfort. So you can achieve the same comfort level by tweaking other parameters. And key variables, I think, in this discussion are air movement, moving air through natural ventilation, which doesn't cost any energy, or moving air through fans. Fans requires much less energy than using air conditioning, or changing clothing. That doesn't cost any energy at all. And as Richard mentioned earlier, Japanese people, they have shown us how far they can actually stretch their indoor air conditioning set point in commercial office buildings just by relaxing their office dress code, which is well known as Cool Breeze campaign. Their office set point in summertime is around 26 to 28 degrees. In contrast, in Australia, we have around 20 to 23 degrees. So like 3 degrees up to 6 degrees difference in indoor temperature. And its energy implication is quite profound. And I hope that answered your question, Julianne.
Absolutely, that was fantastic. Thanks so much, Jungsoo. I think it's really interesting, this whole idea of what we wear influences our comfort. I mean, it's quite a, I guess, simple concept, but it really does have such an impact. And I think we're probably seeing a lot of that in Australia as well, as we start going back to the office, and our kind of dress code has gotten possibly even a little bit more casual since we've all been working from home and just been in Zoom meetings wearing t-shirts and things like that. So I wonder if that's kind of a phenomenon that we're experiencing here as well, similar to what was happening in Japan with that less energy needed to condition spaces in summer when they're wearing cooler clothing as opposed to the whole business suit. But Veronica, I will go to you next. So you've been talking a lot about how the idea of comfort is highly subjective, and ideal indoor temperature ranges for a location or an individual varies based on a wide variety of factors. And you have spoken a little bit already about what your research has uncovered about these aspects of comfort, but I'm wondering what implications all of this has for when we might consider building energy upgrades to existing homes and commercial buildings, or to what degree we might retrofit buildings versus just rely on occupant behavior, and particularly all of this within the context of continued warming due to climate change. So I guess I'm just wondering about the balance of when do we consider upgrades to a building versus when do we rely more on the occupant to take action on their own comfort?
Oh, thanks, Julianne. I think we do need to start with the occupants. We design and we build building for the occupants, right? We don't design and build for the building or for the heating and cooling equipment. So I think we need to, as a designer, we need to remember that people are different. So understanding these differences, I think, are really important. Of course, when we design something for a whole group of people that we don't know who they are, it is a bit more difficult. But I think as much as possible, engaging with the, say, future clients and all the possible users of the building, is really important to understand these differences. And then, of course, we design it accordingly, encouraging people, or by designing the building that would encourage people to be more engaged with the building, because that's what I'm trying to say. In terms of retrofit, I think it's the same thing, that it depends. There's no one size fits all strategy. Again, back to their preference, back to their tolerance. I think the strategy needs to fit within that that objective. The example that I gave, and this is only just for one cohort of older people, which is older people, as you saw before, that we found that there are actually 6 different types of older people, even though we like to say that older people are everybody who's above 65 years and above, but it's not true. It's not one homogeneous group. It's actually quite heterogeneous. So what we suggested is that, at least in the context of South Australia, based on our study, that the guidelines, say, for retrofitting homes should also look at this heterogeneity of older people. If I may, just sharing a screen, which is the thermal comfort at home guideline that we came up with from our study. This is available on issue, or if people want to get the hard copy, I can, soft copy, I could send you the link. But what I wanted to say is, basically, toward the back, we gave examples of scenarios, and there are 6 scenarios, which is based on the 6 clusters that we found. So it really depends on their objectives or their preference. In this case, this, of course, is a hypothetical name. They wanted to have indoor condition that is 24 degrees all the time, and these are some of their problems, some of the constraints. So basically, we use some typical homes from the participants, we do simulation, and then we test so many different options and came up with the results. And we said, okay, if you do this is what could happen. You can save energy by 20%, or your indoor condition would improve by such and such. And then again, if you look at the next page, then you see different again. So these are the person who probably more technological savvy and prefer to use air conditioning for. If that's the case, then the intention would be more improving the envelope, for example, and then getting more efficient heating and cooling system. Another scenario is person who really want to improve the building to become more energy efficient. So again, there are ways of doing it based on what their intentions are. And then this last one, for example, is simply to create more comfortable home. But again, we give them the parameters. If this is the range of conditions that you prefer, these are the strategies that you can implement. And then we also include the cost analysis on that. So that's just some example of, I think, what we could do is to provide possibilities. And again, it in the guidelines that we provided, actually, it involves personal actions as well as improving the building envelope. I think they have to come hand in hand. It cannot be just one or the other.
Yeah, that makes a lot
of questions.
Yeah, absolutely. Thanks, Veronica. I think that makes a lot of sense. I mean, obviously, I think that household occupants need to be given a choice as far as what they want to happen to their home, and how they'll balance that with how they'll behave in the home. But then I guess there's an added complexity point, which we don't need to go into now, but we could later on, which is, one person living in a house now might not be the person who lives there for the entire lifetime of the building. So we might need to design retrofits for buildings to also think about who might live there later, which is just another piece of complexity to the whole puzzle. But I will go to Toby next. So you spoke about the Victorian Healthy Homes Research Project and how there were some experiences of warmth that didn't necessarily correlate with the actual temperature increases indoors, specifically in terms of Victorian winters. Could you talk about a little bit so you spoke about this a little bit in your presentation, Toby, but can you talk a little bit more about how the experience of the occupants of the temperature changes varied from what the actual temperature increase was due to the retrofits? And what does that mean for building retrofits or energy upgrades to homes as a whole? And I'm also wondering whether these findings apply to warmer climate zones in Australia, and thinking about, again, the context of continued warming due to climate change.
So I wouldn't say the subjective and objective necessarily, we didn't see inconsistencies. What I would say is that even small rises in objectively measured temperatures in winter were sitting alongside quite substantial rises in subjective thermal comfort. People felt it was a lot warmer, even though it was only slightly warmer. And I think that's a really important consideration here for all the reasons that others have spoken about. It's like there's plenty of things beyond what your thermometer says that go into your subjective experience of thermal comfort. So as a randomized trial, Healthy Homes, our primary outcome was temperature. So we had a data logger that sat on the wall of the living room of these places, measured temperature every half hour, which was really powerful for us because we could map temperature across the day. We knew when was coldest, when was warmest. I showed that graph showing that the poorest quality houses were coldest, but knowing that objective temperature measurement, we could also show that our upgrade had the biggest effect on temperature in those poorest quality houses. So we know if you're doing a relatively modest upgrade like this, it's best to focus on the 1, 2, and 3 star houses because you'll raise their temperature more than the same upgrade on a 6 or 7 star house. So that really needs to be the focus, and that's objective measurement of temperature was a really strong part of the trial. As a result, it allowed us to investigate lots of different questions. But just as important was asking our householders whether they felt warmer, because ultimately that's the aim. You want people to have that experience of thermal comfort and get the health benefits that come along with that we managed to show as well. Warmer climates, Healthy Homes was totally based around the Victorian winter, so I can't comment too much on warmer climates, but I just point to something Jungsoo said, because I absolutely agree. I think the focus from an energy efficiency point of view should definitely be on creating thermal comfort with fans, because they're so much cheaper and less energy intense to run than refrigerative cooling. And obviously we have very good options with reverse cycle air conditioners these days that are a pretty efficient way to cool your house. But I absolutely think there's a role for pedestal fans and ceiling fans in managing thermal comfort in warmer climates from an energy perspective.
Yeah, that's great. Thanks, Toby. And it sounds like, based on what Veronica showed from her research, that fans are something that people are already employing kind of as the number one option already. So the occupants are way ahead of us in terms of, how they're actually dealing with these things before we even get to the retrofit stage. So just a reminder to everyone in the audience, send through any questions you might have in the Q&A. We do have 2 here, so I will pose those to the panel. So first, Erica Kenna asks, I'm interested to hear what the panel thinks might be good comfort metrics when designing buildings like aged care and hospitals, where occupants are less likely to have the ability to adapt, I guess, through changing aspects of their immediate environment, though they might be able to add things like a blanket or more clothes or things like that. Would adaptive thermal comfort assessment still be relevant, and is it useful as a design tool? I will leave that to whoever would like to answer.
I would like to answer first. Go ahead, Richard. Now go for it.
No, I was just about to dob you in for that one. My off-the-cuff response to that question is that the adaptive comfort model would still be applicable. And there has actually been a resurgence of, how would you put, advanced naturally ventilated healthcare facilities in various parts of the world. And obviously this is related to COVID, but it has implications for thermal comfort as well. And as soon as we start talking about natural ventilation, I think it's the importance of the adaptive comfort approach is blindingly obvious. It's got to be taken into account. So that's my response. I'd like to hand it over to Veronica now. She'll have a much more considered analytical response.
Thanks, Richard. I have to say, I agree with Richard. There is a place for adaptive comfort. But before we decide in any design project, again, coming from design background, I think we really need to understand who we design it for. Now, if we design for aged care, let's start with aged care. It would be good if whoever doing the project try to do sort of, say post-occupancy evaluation of another aged care of the same organization, perhaps, and just watch or see the behavior of the people. Similarly with the hospital. And the reason I mentioned that, we did some study in a hospital and found that even though in terms of, and it's all air conditioned, the range of temperature is within what required. We did evaluation, or we did monitoring, and we talked to the patients, and we look at their clothing, and we saw that in certain part of that hospital, the patients had to put layers and layers and layers of blankets and clothing, and we talked to them, they say it's too cold for them. And what we found is not necessarily just the temperature. Apparently the air is blowing to them. So Jungsoo already said it's about air movement also is a factor. So again, it does show that even though you follow the standard, you use air conditioning, it also doesn't guarantee their comfort if the other factors are not taken into account. Plus, when people can't move much, that becomes even more critical to make sure that what they got is what they need. So I think do that first before then we decide, okay, if we do have to air condition, for example, to maintain certain conditions, yes. However, the other thing also that I still strongly suggest is please still allow the adaptive behavior to take place if need to, because quite a lot of the patients actually said, I prefer to be able to open the window, but if I do that, the nurse will get upset with me because they're not allowed to. But they do want the fresh air. So once again, if you bring it back, put it back to the occupants and really see what they need, we probably would see that they actually prefer to have more fresh air, more naturally ventilated buildings, rather than it's simply about maintaining temperature at certain conditions. So yes, at certain time, you do need to have the air conditioning, but at other times, you probably don't need to have conditioning, because not only just to save energy, but really because the occupants actually don't need it or don't want to. So I think there's a place for both. And it's the same thing in the aged care. I think it's the same. Just one last thing, Julian, if I may, is another possibility. And again, this depends on whether you have the means to do it. As part of the results of one of my previous PhD students who now already graduated, she looked at personal comfort models. So looking at even further than the cohort of people. But if you could look at the personalized, sort of what we call personalized comfort model, where it then based on individual preference, and if we now have smart system in the air conditioning unit, if that can be applied as well, depending on individual preference, that would be even better. And the personal comfort model can be, the model right now is still based on temperature, humidity, and so on, but it could be personal factors such as their body composition can also affect their comfort and so on. And if you could sort of predict that in advance by collecting data first, this is based on machine learning. Sorry, I don't want to be too detailed on that, but you actually could come up with even a more personalized model, which again, the potential of saving energy is a lot more, because then you don't generalize that everybody needs the same thing.
Thanks, Veronica. And Jungsoo, yeah.
I would like to just add one more thing, that personalized comfort concept is, I think, very relevant in the hospital comfort context, because we are talking about meeting the comfort requirement for two different cohorts, that is patients and staff members in the hospital. And their metabolic rate can be quite different, because patients lying on bed, very, very low metabolic rate. Staff working hard, having a busy day, metabolic rate is high. In temperature terms, it could be a few degrees difference between the two cohorts. And we don't even need to go to adaptive model. Even in PMB model, metabolic rate is captured. So, I think the discrepancy in comfort perception in hospital settings is because usually the temperature that makes the staff comfortable is probably the set point temperature. Then the patients might experiencing overcooled conditions. So if that was the case, if you were to apply personalized comfort concept, therefore a bit of controllability according to the comfort requirement, it could potentially push the thermal satisfaction level overall for the entire occupant group.
Thanks, Jungsoo. So Toby, conscious that this question is a little bit more geared towards the commercial building side of things, but did you want to weigh in on the residential side?
No, nothing from me. Nothing from me really. I was going to make the same point that Sue made, and also there's visitors to think about too, who are coming in and out from the outdoor environment, which according to the ASHRAE curve we've seen is going to mean they're probably on a different natural set point as well.
Absolutely. Lots of different groups to think about, even within one setting. So some more audience questions here. So I've got one specifically for Richard. What is your thought, or what are your thoughts on the adjusted PMV metrics suggested in the ASHRAE appendix that takes into the account, this is a very technical question, the sky vault, occupant position, and azimuth, and solar exposure, etc. And maybe the two of you can connect after the session to get into another conversation about this. But if you have a quick response to that one, Richard.
I do. And that is that it's a very technical question, and I won't go into all the gory details, but solar ingress into an occupied space gets incorporated into our models of comfort through what we call the mean radiant temperature parameter. And so that appendix that you're referring to in ASHRAE 55 is about rolling in solar shortwave radiation loads on the body and on the actual surfaces of the room itself, rolling that into the mean radiant temperature calculation, which in turn gets embedded into the operative temperature index. And that's about all I should say. I'm happy to talk offline to that person who made that question.
I think we'll get the two of you connected so you can discuss further. So I want to go to, I do have a couple of audience questions, but in the interest of time and bringing the residential side back into this conversation, do just want to ask a general question to the panel around airflow and draft sealing and ventilation. So I think I'll go to Toby first, just to bring you back in from the residential side. So how did the Victorian Healthy Homes pilot address air movement and ventilation for improved health and comfort outcomes? And also along with that, how do draft ceiling, ventilation, and insulation interact to create an effective thermal envelope to ensure comfortable indoor temperatures? So I think potentially some people in the audience might have a bit of an idea of that second part of the question about how those different pieces interact, but maybe if you could talk a little bit more about how the Healthy Homes pilot focused on that kind of idea of air movement, that would be really great.
Sure. So it's pretty simple, really. We were aiming to increase the thermal shell of homes to trap more heat in them during winter. We know a lot of our homes are leaky, and so there's drafts and gaps around doors, windows, ceilings, floors, and by fixing those gaps, by sealing up those gaps, you stop heat escaping to the colder outdoors. And insulation essentially does the same thing by providing, resistance to that cold air flowing, the warm air from inside your house flowing to outside. So our interventions in Healthy Homes were very much around thermal shells. So for example, we weren't putting solar panels on as part of our upgrades. We were focused on those things that increased your home's thermal shell. So that was insulation and draft sealing. We know they're two of the best things you can do in terms of bang for buck to improve your thermal shell. Window coverings are also really important. So we did install curtains and blinds, and ideally they will have a helmet across the top of them to create that thermal break to keep more heat in, because you really want to trap a still layer of air against your window that isn't circulating through your room. So if you can insulate and draft seal and cover your windows effectively, you are going to retain just much, much more heat in your house, which is going to make you healthier, make you more comfortable, reduce your energy bills. So that really was the focus of our intervention.
Great, thanks so much, Toby. So wanted to go to Jungsoo next and ask a related question around air movement and air infiltration in buildings. So is there, we know that you need to do air sealing in buildings to make sure that, there's not too much air movement, as Toby has been talking about, but we also need adequate airflow to make sure that there's enough ventilation so that we don't cause things like moisture issues, condensation, mold, that type of thing inside buildings. So is there a trade-off between draft sealing and having adequate indoor airflow? And how are these two factors of a building envelope best balanced?
Infiltration or exfiltration, depending on the direction of airflow. And the simple definition in lay language is unwanted air exchange or unintended air exchange between indoors and outdoors. And I hear it all the time from my international students just arrived in Sydney. They often find their accommodation in old terrace house in inner west near the university. And they all complain about how cold they feel indoors and how leaky their accommodation is compared to their homes in Northern Hemisphere, where their winter is much, much colder than that Sydney. But inside the house, they all say Sydney's colder. Leaking homes wouldn't be a big problem as long as the outdoor condition is mild, favorable, or not too extreme, which is the case for Sydney, except for winter months or during heat waves in summer. And having a leaky house is probably a good thing when it comes to indoor air quality, especially for those people or householders who doesn't necessarily practice opening windows for ventilation. But however, back to its original definition, it's unintended ventilation causing unintended heat exchange. It needs to be minimized because otherwise we have to use cooling or heating for a period when it's really not needed. So if you wanted to create airflow, I think it should be done through openings that we put in place on purpose. That's what we call windows and doors. So I don't think drop ceiling and airflow indoor needs a balance at all. Drop ceiling is a good thing, as it will reduce infiltration or energy leakage. But in the meantime, ventilation for better air quality and airflow for better comfort needs to be provided through windows and through natural ventilation strategy, not through infiltration.
Thanks, Jungsoo. So we've got about 9 minutes left in the session. Just wondering if any of the speakers want to go into the kind of air infiltration, ventilation idea a little bit more before I go into one final question.
If I just may add on that issue of ventilation, we do have a challenge, however, in Australia, particularly if you live in more than one-story building, because the building code requires, the National Sanitary Code requires the window to only be open no more than 125 millimeter wide. For safety reason, possibly because it's, you know, the code asks for, you know, like a ball 125 mil. As long as the ball doesn't go through that opening, that's okay. And that is a problem, because how much can you get? How much fresh air can you get with that much opening? And you also just mentioned about students. My own daughter now lives in an apartment in Melbourne, and that's it. That's how much window she can open. And she said it is very stuffy, and so when it's stuffy, she has to turn on the air conditioning, and that is a problem that I think I don't know what the solution is, and it seems to me that people in Australia is too afraid to fall out from the window, whereas people in Europe doesn't seem to have that problem, or Japan or other Asian countries, as you know. They've got windows everywhere. And I think the interesting thing is but if you have a balcony, then you can open 100%. And it always puzzled me because it sounded like people are not going to jump out through the balcony or over the balcony, but people would jump through the windows. It's a bit, puzzling. So that is a challenge, I think, for opening windows, but also the window type, the window opening. We found, particularly back to the issue of older people, a lot of windows are difficult to open because of the design of the handle, especially when people start to have arthritis and so on. They can't easily open the window. So one is a design issue, but the other one also is the standard or the code issue that I think need to be improved if we really want to increase the natural ventilation, a possibility of natural ventilation to improve air quality as well as reduce energy consumption.
Thanks for that, Veronica. Richard, were you wanting to weigh in on that?
Yeah, just following on from Veronica's very sensible comments there. During the COVID period, or actually just towards the end of the COVID period, we were tasked to come up with some guidelines and recommendations for return to schools, many of which were naturally ventilated. And we came up with it was a consensus design target or criterion of a 5% openable area of windows and doors as being desirable for maximum ventilation and fresh air and minimal risks of cross infection from kids. Now, achieving a 5% openable area, that's referencing the floor area. So you've got to have as much of 5% of the floor area of the room as openable on the windows. Very hard to do with this National Construction Code restriction on how far you can open windows. So I don't know what the answer is. A compromise might be just a complete change in the way we think of windows, and probably louvers would give you a much larger openable area and still comply with the restrictions.
Mm.
That's all I can think of.
Mm. Yeah.
Thanks, Richard. I do have a question in the Q&A from Mike Dodd, but I think we will save that for the session after the webinar. Mike, I hope you are coming to that. So we will save that as it's a bit more of a technical question. We've got 5 minutes left. I just want to pose one last question to all of the speakers. Maybe if you can just give me your 1 minute answer on this. So I introduced the session with the kind of tension between optimally retrofitting all of the buildings and the fact that we might not successfully achieve that goal. And we definitely, either way, need to think about occupant comfort in terms of people's own control over their own environment and how they control their experience within the building, whether or not it's optimally retrofit or not. So as we continue on and we do some retrofits here and there, but we haven't been able to reach all of the building stock. I'm wondering what each person's priority is, or what you think our focus should become for reducing energy consumption and maximizing comfort as much as possible within buildings, as we're going along and attempting to do more energy upgrades, but maybe they're going a bit more slowly than we had hoped. I'll leave that. If anyone wants to jump in, hopefully we can get to all of you in the next few minutes. Any thoughts? Yeah, Richard, please.
I can talk to a paper that we published in the Lancet Planetary Health Journal last year that ranked the greenhouse abatement potential of a whole bunch of strategies. And one of them that we were particularly focused on in that paper was increasing airspeeds within buildings. And it came out as one of the best bang for buck strategies, comparable to compact fluorescent light globes and LEDs in terms of bang for buck. So that's my forecast. I think that's where we're going.
I am muted, of course, 2023, here we are. Thank you for that, Richard. Did someone else want to jump in on that point before we wrap up?
Yeah, maybe I can just give some context in the Victorian situation. Anyway, Julianne, it's great in the new building space that we're moving from 6-star to 7-star, but I think we shouldn't forget that we have this legacy of older buildings. Victoria has 1.3 million homes that were built before 1991 when any energy standards came in, and we know they average less than 2 stars. So we have this legacy building stock that we need to do something to improve so that people aren't unhealthy and spending lots of money heating and cooling their home. And our results are pretty compelling in showing that we should be aiming at the 1- and 2-star homes, because even boosting them by a star or two with a pretty minor upgrade leads to much better outcomes. So I think that's where the focus needs to be.
Thanks, Toby. Absolutely agree on that point. And Veronica, did you want to go next?
Yeah, well, look, of course, improving energy efficiency is very, very important. But at the same time, I think we need to balance that with ensuring that while doing that, that we also ensure the indoor air quality is improved, because currently the way we assess energy efficiency of buildings, it is by predicting heating and cooling, implying that there will be heating and cooling. Isn't that better or not better? Another way of looking at it, perhaps by saying, could the house even be healthy and it's good for the occupants if heating and cooling are not even needed? And therefore, the thinking is become then different, because then the design strategy, because you could still have very energy efficient building with, let's just say, very little windows. As long as windows are very efficient, high rated and so on and so forth, a lot of insulation, and you might end up having building with very little energy with windows that don't necessarily open. So that's sometimes it worries me when we focus too much on energy efficiency without looking at the indoor environment quality, the impact of the people. So I just hope that we can balance that we address both at the same time.
Thanks, Veronica. And Jungsoo, do you want to weigh in the final word on that question?
Yeah, having energy efficient house is important, but in the end, it's people who spend that energy. So no matter how efficient building is, if that is operated by inefficient people, it's end up being an inefficient building. I'm saying this because Richard and I and our team has been collecting, monitoring how people operate the buildings in Sydney and also in Southeast Queensland. And I get to observe lots of energy wasteful behavior. For example, leaving air conditioner on in an empty house, and the tendency goes up when it gets warmer outside. So presumably that is because people can't even tolerate a few minutes of discomfort when they first arrived at home. So they run their air conditioner all the time. And I get to observe quite frequently air conditioners turned on with windows wide open. So these behaviors are certainly not very efficient. So we need to kind of look back and how we behave and what do we do to achieve energy efficiency in households.
Great, thanks so much, Jungsoo, and thank you so much to all of our speakers, and thank you for everyone for attending the session. I will wrap it up since we are a minute over time, but again, just wanted to thank our speakers Veronica, Richard, Jungsoo, and Toby for joining us today, and thanks for all who attended. Would also like to thank again the Department of Climate Change, Energy, the Environment, and Water for supporting this session, and thanks to Nat from the EEC for all of your help in the background.